This is our second lecture. It will be part 2 of stable matching. So we went over the algorithm last time, but we'll start this time with doing a little simulation since we didn't do it before. It's a little bit long and tedious, but it's probably still worth going through to make sure that your intuitions about what the algorithm does are correct. So here's an instance with 5 hospitals and 5 students and their list of preferences. Okay, so we begin with some unmatched hospital making an offer to a student. And let's just suppose that Atlanta makes an offer to Wayne or proposes to Wayne, right? So Atlanta makes an offer to Wayne. Wayne isn't matched, of course, since nobody is yet. And so Wayne accepts the offer and Atlanta and Wayne become matched. Next, suppose that Boston proposes to Yolanda. So again, of course, Yolanda is not matched yet, so accepts the offer. So we wind up with this matching. Okay, so suppose next Chicago proposes to Wayne. It's here. Now Wayne is already matched with Atlanta, but prefers Chicago. So Wayne will accept Atlanta's offer and reject Chicago. So now we have this partial matching, this matching with Yolanda and Wayne. And Atlanta now is unmatched, but Wayne has been removed from the list of candidates to make an offer to. Okay, so next, suppose Atlanta proposes to Val, right? The next student in their preference list. Okay, what happens with Val? Well, Val's not matched with anybody, so she accepts the offer, and we get to this matching. Okay, suppose next Detroit wants to make an offer and makes an offer to Val. Now, of course, Val is already matched with Atlanta, and Val prefers Atlanta to Detroit, so rejects Detroit's offer. Okay, so nothing changes with the matching, but we do note that Detroit essentially removes Val from their list, right? Okay, so next, suppose Detroit then proposes to their second ranked candidate, Yolanda. So what's the status of Yolanda? Well, Yolanda is currently matched with Boston, but prefers Detroit. So she'll accept Detroit's offer and reject Boston. And so Boston now becomes unmatched again. So we have this matching and Yolanda removed from Boston's list. Okay, so suppose Boston proposes to their next preferred candidate. That's Wayne. What's the status of Wayne? Well, Wayne is matched with Chicago. Wayne is happy with Chicago, prefers Chicago to Boston, so Wayne will reject that proposal. Okay, suppose Boston next proposes to Val. Well, Val is matched with Atlanta and prefers Atlanta, so Val will also reject Boston's offer. Boston now proposes to Xavier. Then we look at Xavier. Xavier's unmatched, so we'll accept Boston's proposal. So we now have this matching. Okay, suppose now El Paso proposes to Wayne, right? It has to be to Wayne because Wayne's the first on El Paso's list. And what's Wayne's status? Well, Wayne's matched with Chicago and prefers Chicago, so Wayne will reject that offer. Next, El Paso will propose to Yolanda. Okay, Yolanda's matched with Detroit but prefers El Paso, right? So she'll reject the Detroit, accept the El Paso offer, and now we're at this matching, where Detroit is unmatched and Val and Yolanda are gone. So Detroit's next candidate is Xavier. Detroit's the only unmatched hospital at this point. So the next offer has to be from Detroit, and it has to be to Xavier, right? The next candidate in Detroit's list. Okay, so Detroit proposes to Xavier. Xavier is already matched with Boston and prefers Boston to Detroit, so rejects Detroit's offer. So next, Detroit proposes to Wayne. Wayne similarly is also already matched and is matched with Chicago, which is preferred for Wayne, so rejects Detroit's offer. So finally, Detroit proposes to Zeus. Zeus is unmatched, so accepts the offer. And now we have this matching, right? Atlanta to Val, Boston to Xavier, Chicago to Wayne, Detroit to Zeus, El Paso to Yolanda, right? And that is a total matching, and it's a stable matching. So we're done. No, total matching, perfect matching. And that's also a stable matching. So we're done. Okay, so now we want to look at a few properties of this algorithm. And so we might ask some questions. So one is, this is a non-deterministic algorithm, right? There's a step that says, take some unmatched hospital and make a proposal. It's clear who the proposal has to be to, the next member of their next ranked member of their list that they haven't proposed to. But any unmatched hospital could go next, right? So you might wonder if that choice of hospitals affects the outcome. So the question is, do all executions of the algorithm lead to the same stable matching, right? On a particular input, you have lots of different possible executions depending on which hospital is chosen at each iteration of the main loop to make an offer. Okay, and here's some possible answers. No, because the algorithm is non-deterministic. Or no, because an instance can have several stable matchings. So they kind of have to be related, right? It could have several stable matchings, but if it wasn't non-deterministic, it would still pick the same one every time. Yes, because each instance has a unique stable matching. Well, that's not the case. There are lots of instances with many stable matchings. And D, yes, even though an instance can have several stable matchings, and even though the algorithm is non-deterministic, it always produces the same solution. And that's actually the correct response. Let me put a red check mark there. That's the right answer. And now this, I think, is not intuitively clear. In fact, it maybe even seems a bit surprising. I think it's not at all obvious that should be the case. And so we want to look at why and what maybe the implications of that are. Okay, so we'd like to understand the solution produced by the Gale-Shapley algorithm, assuming now that I'm not lying and that there is a solution that it produces for any given instance. So first, let's just observe that for a given problem instance, there can be several stable matching. So here's a very small instance, right? 3 hospitals, 3 students. And we can see easily that there's 2 stable matchings. And I've colored them so you can see them easily, right? One where with X to A, B to Y, and C to Z. And the other one in pink with X to B, Y to A, and again, C is to Z. Okay. So now we want to understand this particular solution, and we're going to use the notion of a valid partner and a best valid partner or worst valid partner. So student S is considered a valid partner for hospital H if there's any stable matching in which H and S are matched. Okay, so what are the valid partners in this example? This is the same example from the previous slide. Okay, so in both stable matchings, and these are the only two stable matchings for this instance, Z and C are matched, right? So Z is the only valid partner for C, but X and Y are both valid partners for A, right? There's a solution where A is matched with X and a solution where, where B is matched with X. And similarly, both X and Y are valid partners for B. Okay, now, as I said, we're going to use the notion of best and worst valid partners. So very quickly, here's a bigger example. I'm not going to go through details, but we want to know who the best valid partner for W is. There are 6 stable matchings here, and we're looking at W. So there's a stable matching with A and W. There's a stable matching with B and W. There's a stable matching with C and W, and there's actually 2 with B and 3 with C, but there's no stable matching with D and W. Okay, so D is W's preferred partner, most preferred partner, but A is the best valid partner for W, right? Because there's no stable matching where D is matched with W. Okay, now let's define a thing that we'll call the hospital optimal assignment. We're not going to call it a matching because we don't know if it is until we check. Right. So the hospital optimal assignment you construct as follows. For each hospital, assign to that hospital their best valid partner. That is, their most preferred student that appears in any stable matching with them, matched with them in any stable matching. Okay. And now the question is, what does this thing look like? So it could be, maybe you have a hospital H, and their best valid partner is S, and maybe there's another hospital, J, and that hospital's best valid partner is also S. If that's the case, then this is not a matching, right? There'll be some other student here who's not matched with, right? So it's not a matching, and not everybody is, not every student or every hospital is not every student is necessarily included. And the second question is, even if it is a matching, is it guaranteed to be stable? And what we'll do is we'll prove that, in fact, the output of any execution of the Gale-Shapley algorithm is a hospital optimal assignment, the hospital optimal assignment. It follows, since the Gale-Shapley algorithm always outputs a stable matching, that this hospital optimal assignment is, in fact, a stable perfect matching. Okay? So how are we going to see that? Well, we'll do a proof by contradiction. Okay, so we want to show that the Gale-Shapley matching, call it M star, is hospital optimal. Okay, so suppose there's a hospital that in the output the Gale-Shapley algorithm gives is not matched with their best valid partner. It's matched with some other student. Okay, now we know that hospitals propose to students in decreasing order of preference. And so if a hospital is matched with a student that's not their best valid partner, it must be that they were, before being matched with that student, they were rejected by a partner they previously proposed to, right? Who is a preferred partner. Okay. So some hospital is rejected by a valid partner. Okay, that could happen many times, okay, during a run. So let's consider the very first time. So we'll run the Gale-Shapley algorithm, consider the very first time that some hospital is rejected by a valid partner, okay? And let's let H and S be the hospital and the student involved in that rejection. Now, H and S are not matched in M star, the output of the algorithm, but they are matched in some other matching, some other stable matching, right? So let M be that stable matching, some stable matching where H and S are matched, right? Okay, so that's here. And now think about the moment when S rejects H. So the algorithm is running. It's going to end up producing this matching, right? But it hasn't got there yet. So it's executing. And the moment when S rejects H looks like this. Right after the rejection, so S rejects H, why? Because either H proposes to S, but S is already matched with some H prime and prefers the H prime, so rejects H. Or H and S are already matched, okay, but then H prime comes along and makes a proposal to S, and S prefers H prime, so rejects H. We don't know which of those two happens, but what we know is right after that happens, we have something like in this picture. S and H prime are matched. And the reason is that S has just rejected H in favor of H prime. So what do we know? Well, we know that S prefers H prime to H. Okay. So that's the first fact. Now let S prime be the partner of H prime in M, right? So let's go to our stable matching M, okay, where H and S are matched, okay? And take this H prime. H prime is matched there with some other student, S prime. Okay? So H prime S prime is a valid partnership, right? Okay, so what do we know there? We know at this point H prime is matched with S, so has already proposed to S, right? H prime is not matched with S prime. And since there's been no rejections of proposals before this moment, except for S rejecting H, we know that S has not rejected H prime, and therefore H prime hasn't even proposed to S prime. Okay, so H prime hasn't proposed to S prime, but has proposed to S. So it must be that H prime prefers S to S prime, right? H prime prefers S to S prime. Okay, put those two facts together, and what we have is that H prime S, this pair here, is unstable in M. That's a contradiction because M is assumed to be a stable matching, right? Okay, so it can't be that any hospital is matched with a student other than their best valid partner. So the Gauss-Shapley algorithm, although it's not obvious, always produces as output a stable matching in which every hospital is matched with their best valid partner, the best student they could possibly be matched with in a stable matching. Okay, so we've established that. What about the students? It sure seems like this should be bad for the students, or at least some of the students, right? And in fact is. So let's define another special assignment, the student pessimal assignment. So we take each student and we assign them to the hospital that's their least preferred hospital among all hospitals that appear that they can be matched with in a stable matching. And so we'll claim now Gauss-Shapley actually finds a stable matching that's student pessimal. Okay, how? It's a little simpler. Okay, so suppose H and S are matched in M star, but H is not the worst valid partner for S. Then there must exist a matching M in which S is paired with a hospital say H prime, that S likes less than H. Okay, so here's M star. We have H and S matched, but they're not, but H is not S's worst valid partner, right? So we know there's some other matching, some other stable matching, okay, in which S and H are not matched, right? And in particular, S is matched with some H prime that they like less than H. Okay, let S prime be the partner of H and M. Okay, so we have H, this is the same H, right? And it's matched to something other than, some student other than S. Okay, call that student S prime. Okay, now what do we know? We know that by hospital optimality, which we proved last slide, S is the best valid partner for H, right? Because this is the output of the Gale-Shapley algorithm. So S is the best valid partner for H, right? That means H prefers S to S prime. Okay, so we have H prefers S to S prime, S prefers H to H prime, put them together, and we have that H and S is an unstable pair in M. So this M doesn't exist. Okay, that's a contradiction, right? And so it must be that if HS appears in M star, then H is S's worst valid partner. Okay, so that's something that doesn't seem to be a very desirable feature unless you want a highly biased algorithm. But that's an important kind of step in understanding the algorithm and where you might or might not want to use it, perhaps. Again, the next thing we want to do is consider efficient implementation, right? So we're talking about the algorithm, but we want to know the time complexity of the algorithm. And in many cases, an efficient implementation of an algorithm, whether you're talking a theoretical implementation, as we're doing most of the time in this course, or a real one, actual code, you typically need careful choice of data structures to perform certain of the operations efficiently enough for the algorithm to be executed as efficiently as you can. So here, let me just run through quickly again what the algorithm is, a reminder. Let me pick a different color so I don't mess things up too much. Okay, so we input our preference lists. And then as long as some H is unmatched, we pick an unmatched H, right? We pick its most preferred student that it's not proposed to yet. Okay, if the student is unmatched, we add HS to the matching. If it's matched, then we check whether the student prefers H or H prime, say the thing the hospital previously was matched with. Okay, and then either we replace the pair HS, so H prime S in the matching with HS, and H prime becomes unmatched, or S rejects the offer. Basically, nothing changes. Okay, so the input has two n squared values, right? Two n lists of rankings, or two n ranking lists of length n each. Okay, so we know we have big O of n squared iterations of the main loop at most. And we haven't proven it, but intuitively it seems like you might have to carry out a large fraction of these possible proposals. So we probably don't expect to do significantly better than big O of n squared time. But we want to do at least as well as big O of n squared time, right? And for that, we need to do each of these operations in the loop in big O of 1 time. And that's why we need to give a little bit of a thought to our data structures to do that. Okay, so what do we need to do? So I've colored them, the lines of in the pseudocode with colors to correspond to the data structures that we need to execute these operations, right? So the first thing we need to do is we need to check if there's an H unmatched, to obtain some unmatched H, and possibly to put some H back, right? To take some H that has been matched and make it unmatched again. Okay, so we need something that holds our collection of unmatched hospitals, and we need to be able to remove an element or add an element in big O of 1 time. So this is not very hard, right? We need a list of unmatched hospitals. We could use a linked list, or we could use an array-based list that operates either as a stack or a queue. We have either way, we can have big O1 insertion and removal because the order doesn't matter, right? We just need to pick some unmatched hospital. Okay, so the next thing we have to do is we have to get the most preferred student for a given hospital H that H is not proposed to. So we'll do more or less what we were doing in our diagrams describing the simulations, right? We need to keep a rank ordered list of the students for each hospital and a next student for each hospital, right? For each hospital, the next student that needs to be proposed to, if that hospital makes another proposal, right? Okay, so there's kind of two obvious ways to do it. We can have an n by n array carrying the list of preferences and an n by 1 array indexing the next student to be proposed to, right? Or we could have an n by 1 array of linked lists, with the linked lists being the students in rank order, and an n by 1 array of pointers, right? Each pointer, the pointer for hospital H pointing to the student that they are next going to propose next to if they make another proposal, right? So that's straightforward. Okay, and then we need to check if a student is matched currently and who they're matched with, right? What hospital they're matched with. Okay. Okay, so the current match for each student, we can put that in, we can have an n by 1 array, right? For each student, we have a element of the array. And in that array, if the student is matched with a hospital, we store the hospital. And if they're unmatched, we have some special value. I've written a bottom symbol here, but it doesn't matter what we call it. We have a special value that indicates it's not matched, right? Okay, so this data structure also takes care of managing the matching, right? If we want to add an HS pair, then we store H in the array element for S, right? And if we want to remove a pair, we replace a pair HS, we replace the H in the location for S with the bottom symbol. Okay, and finally, we have to check if S prefers H and H prime. So this is the only one that requires a little bit of work, different from, say, what kind of looks obvious when we just write the simulation on the slides, right? But it's, so it requires a little manipulation of the data after we input it, if we input it in the rank ordered lists, right? But it's pretty straightforward with an n by n array of student rankings, right? Where R of S and H is the rank of hospital H for student S. Then given student S and 2 hospitals in H and H prime, we have 2 lookups in the array to decide which, to find the preference value for each, ranking for each, and compare them. Okay. Another little collection of questions. Suppose each agent knows the preference lists of all the other agents, okay, before the algorithm is executed, okay? And so imagine you know that, maybe you can trick the algorithm by lying about your preferences if you know everyone else's preferences, okay? So which of these is true? A, no hospital can improve by falsifying its preference list. Well, the thing about the hospitals is they get their best valid choice, right? Their best valid matching. So if they were to lie, they might not get their best matching, but they can't do any better. Okay. So by falsifying their preference list, they can't make things better. They are already doing as well as they can possibly do. The student's a different situation. Okay. So can a student improve by falsifying their preference list? And I don't have a proof at hand, but sometimes they can. Right? And so sometimes a student can improve. So intuitively, you can imagine, the student knows that they're going to get their worst possible choice. If they know everyone else's preference lists, they may be able to lie, right? So they don't get stuck with, suppose there's a hospital that really likes them, but they don't want to go to that hospital. If that hospital makes them an offer right away, they may never get to change, right? But if they know everyone's list, they may be able to lie about their preferences to make sure they get an offer from another hospital. Okay, both A and B, obviously, they if one of them is true, false, obviously both of these are false. Okay, so it's easy to think up lots of variants and exceptions and extensions to this problem. In fact, there's a literature on generalizations and variations of stable matching that continues to grow today, even though this problem and this algorithm are very, very old. People continue to study variations. So let's just consider some very elementary one, right? Suppose some agents declare others unacceptable, or some pairs are unacceptable, right? If you think about a stable matching, then there are certain pairs who are not allowed to marry, right? Or in the medical school example, maybe there's particular students who simply are going to refuse to go to a certain hospital. And the second one is, so suppose hospitals have more than one position. So maybe one hospital has only one position for a resident, but some other hospital has 10. Right. So what happens then? Well, if we just generalize the definition of unstable a little bit to take into this account, right? So a matching here is unstable if there's a pair that are acceptable to each other, okay? And either S is unmatched or S prefers H to its assigned hospital, okay? And either H does not have all its places filled or H prefers S to at least one of its assigned students, then it's unstable. Okay, well, it turns out, and we're not going to prove it, but with a little bit of work, you can easily generalize the algorithm. And it's pretty easy to see what the steps are, right? A hospital, so instead of an unmatched hospital making a proposal, you just have a hospital that doesn't have all its positions filled, gets to make an offer, right? And offers to its most preferred student that it hasn't offered yet. Okay, and a couple of other tweaks. And it will find a stable matching. Okay, there's a little caveat. It might not be a perfect matching anymore because these having unacceptable pairs might make it impossible to have a perfect matching. I mean, you could think of a very simple case. There's a student who just refuses to go to any of the hospitals. It's a bit stupid, but you won't have a perfect matching. Okay, just a couple of tidbits to finish up, right? So the Gale-Shapley algorithm was introduced in 1962, but a very similar method, essentially the same method, was being used since 1952 in actual med school hospital assignment, med student hospital assignment work. Okay, and various interesting things happened. For example, it was revised in 1998 to make it med school student optimal instead of hospital optimal, because presumably they felt that overall outcome would be better if the students were happy. Okay, and there's a paper talking about that. One of the authors here you'll notice is this guy. And I point that out because in 2012, a Nobel Prize for Economics was awarded to Shapley and Roth, exactly for this algorithm and the theory behind this algorithm. So this is considered to be a pretty substantial contribution to economics. Okay, this is just one of many examples. This is a paper about network-based, web-based content delivery and application of generalizations of this algorithm there. And there are lots and lots of others. As I said, there are lots of variants of this problem that continue to be studied today. And that's it for now.